Hello, in this short video we're going to look at Nobel Prize in Physics for the year 1910 awarded to Johannes van der Waals for his work on the equation of state for gases and liquid. We're going to look at some of his work and some biographical elements and at the award-winning speech. And in the next video we will deal with his Nobel Prize lecture. Here you see his diploma, which he received when you win a Nobel Prize. First, some work details coming from the official Nobel Prize site. As you can see, follow this link and you see this. The matter around us assumes different forms, solid, fluid or gaseous. The relationship between the volume, pressure and the temperature of gases has been formulated since the 17th century. In 1873, Johannes van der Waals formulated an equation of state that applies to both gases and liquid. In it, he introduced the idea that molecules attract one another to explain why the laws governing gases do not apply under high pressure. In 1880, he formulated the principle that a gas can be fully described if the critical temperature at which the gas liquefies is known. Then some biographical elements coming also from the official Nobel Prize site, which is summarized by me. It's not complete. If you want a complete biographical information on that site, follow the link, which we will see further on. In 1873, he, that's of course van der Waals, obtained his doctor's degree for the thesis entitled Over de continuïteit van den gas en vloeidstoestand, that is Dutch, on the continuity of the gas and liquid state, which put him at once in the foremost rank of physicists. In this thesis, he put forward the equation of states, embracing both the gaseous and the liquid state, and he could demonstrate that two states of aggregation not only merge into each other into a continuous manner, but they are in fact of the same nature. The importance of this conclusion from van der Waals' very first paper can be judged from the remarks made by James Clerk Maxwell in Nature, that there can be no doubt that the name of van der Waals will soon be among the foremost in molecular science. The immediate cause of van der Waals' interest in the subject of this matter was R. Clausius' treatise, considering heat as a phenomenon of motion. This led him to look for an explanation for T. Andrews' experiments from 1896, revealing the existence of critical temperatures in gases. It was van der Waals' genius that made him see the necessity of taking into account the volumes of molecules and intermolecular forces, so-called van der Waals forces, as they are generally called. This in establishing the relationship between pressure, volume and the temperature of gases and liquid. A second great discovery was published in 1880 when he enunciated the law of corresponding states. This showed that if pressure is expressed as a simple function of the critical pressure, volume as one of the critical volume, and temperature as one of the critical temperature, a general form of the equation of state is obtained, which is applicable to all circumstances, since the three constants A, B and R in the equation, which can be expressed in the critical quantities of a particular substance, will disappear. It was this law which served as a guide during experiments which ultimately led to the liquefaction of hydrogen by de Waal in 1898 and of helium by Kamerlingh-Onnes in 1908. 10 years later, in 1890, the first treatise on the theory of binary solutions appeared. By relating his equation of states with the second law of thermodynamics, in the first form proposed by Gibbs, in his treatise on the equilibrium of heterogeneous substances, he was able to arrive at a graphical representation of his mathematical formulas in the form of a surface, which he called the psi surface, in honor of Gibbs, who had chosen the Greek letter psi as a symbol for the free energy, which he realized was significant for the equilibrium. The theory of binary mixtures gave rise to numerous series of experiments, one of the first being carried out by J.P. Kuenen, who found characteristics of critical phenomena fully predictable in the theory. Lectures on the subject were subsequently assembled in the Lehrbuch der Thermodynamik, that's Deutsch, German, textbook of thermodynamics by van der Waals and Koonstam. Mention should also be made by van der Waals' thermodynamic theory of capillarity, which in its basic form first appears in 1893. In this, he accepted the existence of a gradual, though very rapid, change of density at the boundary layer between liquid and vapor. a view which differed from that from Gibbs, who assumed a certain transition of the density of the fluid into that of the vapor. In contrast to Laplace, who had earlier formed a theory on this phenomena, van der Waals also held the view that the molecules are in permanent rapid motion. Experiment with regard to phenomena in the vicinity of the critical temperature decided in favor of van der Waals concepts. Well, here is the link I spoke about earlier. If you follow this link, you will come to the official Nobel site and you can read the full biography, not the summarized version I gave here. Here you see a graph with horizontal the volume and vertical the pressure of a gas, and you can see the lines and the gas formula. Pressure times velocity is a constant, times the number of molecules, times a constant, times the temperature of the gas in Kelvin, not in Celsius degrees. And you see earlier empirical gas laws which were pre-van der Waals. Boyle, Charles, Avogadro, Gay-Lussac, they lived earlier. Well, you can see them here. If you want a more detailed look at them, pause the video or go to this Wikipedia page. Then the award ceremony speech by Professor O. Mantellius, also, of course, coming from the official Nobel site and again summarized by me, so the original is longer. As far back in his inaugural dissertation, The Relationship Between the Liquid and the Gaseous State, van der Waals indicated the problem to which he was to devote his life's work and which still claims his attention today. This is 1910, today. In the dissertation to which I have referred, he sought to account for the discrepancies from the simple gas laws which occur at fairly high pressure. The simple gas laws, we saw them net on the Wikipedia page. He was led to the assumption that these discrepancies are partly associated with the space occupied by the gas molecules themselves, and partly with the attraction which the molecules exert on one another, owing to which the pressure acting on the interior of the gas is greater than the external pressure. These two factors become more and more pronounced with increased compression of the gas. At a sufficient high pressure, however, the gas becomes liquid unless the temperature exceeds a certain value, the critical temperature, as it is termed. Van der Waals shows that it is possible to apply the same considerations and calculations to liquid as to gases. When the temperature of a liquid is raised to beyond the critical temperature without the liquid being allowed to volatilize, it is in fact converted continuously from a liquid to the gaseous form, and close to the critical temperature it is possible to distinguish whether it is a liquid or a gas. The force preventing the separation of the molecules in a liquid is their mutual attraction, owing to which a high pressure prevails in the interior of the liquid. Van der Waals calculated this pressure, the existence of which had already been vaguely perceived by Laplace for water. It amounts to not less than about 10,000 atmosphere at normal temperature. In other words, the internal pressure, as it is called, of a drop of water would be about 10 times greater than the pressure at the greatest depth of the sea known to us. However, this was not the most important result of van der Waals' studies. His calculations led him to consider that once we are acquainted with the behavior of a single type of gas and the corresponding liquid, that is of carbon dioxide, at all temperatures and pressures, we are able by simply proportioning to calculation for any gas or liquid its state at any temperature and pressure, provided that we know it at only one, that is the critical temperature. I also said here that is, for instance, that is. Sorry. On the basis of this law, we are known as corresponding states for various gases and liquids. Van der Waals was able to provide a complete description of the physical state of gases and, more important, of liquids under varying external conditions. He showed how certain irregularities can be explained, which had earlier been found by empirical means, and he devised a number of new, previously unknown laws for the behavior of liquids. It appeared, however, that not all liquids conform precisely to the simple laws formulated by van der Waals. A protected convergency arose around these discrepancies, which were ultimately found to be attributable to the molecules in these liquids, not all being of the same character. The older van der Waals laws apply only to liquids of a uniform composition. Van der Waals then extended his studies to mixtures of two or more types of molecules, and here too he managed to find the laws, and these, of course, are more complex than those which apply to substances composed of molecules of a single type. Van der Waals still occupied with working out the details of these great investigations. Nevertheless, he has successfully surmounted the difficulties that were initially in his path. Van der Waals' theory has also been brilliantly successful through its predictions, which made it possible to calculate the conditions for converting gases into liquid. 2 years ago, Van der Waals' most promising Kabeling honors in this way succeeded in compelling helium, the last previously uncondensed gas, to assume the liquid state. Van der Waals' studies have been of the greatest importance not only for pure research. Modern refrigeration engineering, which is nowadays such a potent factor in our economy and industry, bases its vital methods mainly on Van der Waals' theoretical studies. As said, this is a summary. If you want to read the complete lecture, you have to follow this link. Here again you see an illustration. Here you see 4 isotherms. That means that the temperature is the same. Horizontal, again, volume, and vertical, the pressure. And here, of course, you see the difference with the earlier graph. Here, this is under great pressure. So the corrections by Van der Waals apply here, and you can see that the difference in the form of the graph. Not with this one, but with the others. If you want to study this more in detail, go to the Wikipedia, where this is from. Here's the link. And there's another, this time the temperature versus the pressure. Also, if you want to continue your study, go to this, follow this link and go to the Wikipedia page where this came from. Okay, this is it for the moment. Next time, this is next week, we will go again into this Nobel Prize and then with the Nobel Prize lecture given by Van der Waals, of course, on this subject.